So hello guys. Today we are going to understand or learn normal modes in 3D sound wave. So before going to 3D, I want to just introduce a little bit of how sound wave, normal modes of sound wave in 1D. Uh, you have studied in your 12th or 11th class. So for recap, I have drawn a diagram. You can see there is this white is the wire which is inextensible, which is connected to two rigid walls here, and I have drawn some modes of the sound wave. You can see this is the largest wavelength mode, and after that, that one the second largest, and so on. So we used to derive that frequency for every wave, like some this way. Here I have written for every wavelength relation with the length, which length L is the length of the wire. As you can see, for largest wavelength, L equals to lambda over 2, as it is not the complete wave, so it is lambda by 2, as it will be complete if we draw like that. And this whole length will be lambda 1, so that will be 1 more L. So we get this equation lambda 1 equals to 2L, and we did so on for other modes. You can pause the video and check these relations. So after that consider the velocity of sound is c and frequency is f. Then we know that velocity equals to wavelength times frequency, and from this expression we get f equals to c over lambda, and we use these relations to find the frequency for every modes of sound wave in 1D, and we get like f1 is c over 2l, and f2 equals to c over 12 times 2, and f3, and so on. So we generalized this expression of frequency and we get this frequency expression of frequency in general for nth mode. So we get this expression for, and n equals to 1 2 3 dot for. So now if we try to find for the normal modes in 3D, that will be like that. If you consider it was a string which was one dimensional, but if you try to find the normal mode of sound wave in 3D, which is the realistic situation, let's say you have a box. Let me draw it here. So you have a box in 3D like this, x and z, and this length is lx, this will be ly, and this will be lz. Let's say for the generalized case, these three lengths are not equal. Then you can have three kinds of modes here, because you can have a wave along this direction. You can have a wave in this direction. You can have a wave in this direction as well, from top to bottom, like I mean from screen to inside the screen there will be wave in this direction also. So uh, how we going to do this, and what will be the relation among them? So to do that, we have to know that wave equation in 3D, wave equation in 3D, and we have to know the method of solving differential equation, which is separation of variable, to get a profound relation of frequency with the modes, as it's in only one direction we can have for as Lx, Ly and Lz are different, so for every direction we are going to have one mode. So then there will be nx, ny and nz, which will run from 0, 1, 2 and 3. So to get the frequency of 3D wave, we have to solve the wave equation for this system. The wave equation for sound wave is given by L square equals to, let me L square psi. This is a Laplacian. This symbol is Laplacian, and psi is the wave function we are going to consider for sound wave. This is the wave expression of wave. So there will be velocity. I missed it, and it will be 1 over. Let me write it here. And using the separation of variable method, and here psi is the function of x comma y comma z and t, sorry, z and t, because wave is propagating in 3 dimension, and so, and using this idea of separation of variable, we can write psi x comma y comma z t equals to t of t. So plugging this expression into this equation, we can write 1 over c square times x y g d2 dt equals to, and in Cartesian coordinate, expression of Laplacian is given by, and using this expression here, uh, we can write, expanding this, I have to shoot this one. I can write plus x times j d2 y divided to plus x times y times d2 times z2 and dividing this whole equation by x y z t, we are going to get c square times d2t dt2 equals to 1 over x d2x dx2 plus y d2 plus 1 over g. So now, uh, according to the rules of separation of variable, as it is a function of only x, this is a function of only y, and is a function of only z, and it's function of only t. So we can, and this is constructing a equation h t x y and z all are independent variable. So for each of the variable we can consider to consider that this expression equals to some constant. Let's say we are considering it equals to this equals to minus kx square, which is constant, and for this one we are considering minus ky square, and for this minus kz square. I'm writing this considering kx, ky and kz because later we will find that these are the wave vector along x, y and z. In general, wave vector will be like this: kx, kx x cap plus ky y cap plus kz z cap. So if we consider like that, you will get that. Let me solve for x component only, then we'll consider for y and z similarly. Let's say for x we can write it like this: x into x dx2 equals to minus ky square as we considered there. So I can write, sorry, it will be x, and you can see that this is the equation of simple harmonic oscillator. So the solution we can write in the complex plane like this: x equals to x over some constant, let's say ax, and e power minus ikx plus bx to the minus ikx x. So this will be the solution for sound wave along x direction, or we can write it in the sine and cosine form like some a prime x cos kx x plus x prime sine k x. So as we considered here, let me draw it again here. We have to use boundary condition to find kx, and let me solve for others. We are going to get similar expression for y and z. Let me write here. Y will be some constant times cos ky times y slash constant, and we are going to sin ky and for z also we are going to get z equals to kz and plus sin kz times z. And let me draw the 3D box here again. Mm, and so now see that whatever be the wavelength or wave you have, it has to be along y direction. And like so, whatever be the wave of frequency or wavelength, it has to be zero. Amplitude has to be zero along this direction. If you have a wave and along y direction, then it has to be zero here. This is the axis, let's say. Mm, it has to amplitude zero or whatever be the same. It has to be zero again here and again here. So it cannot be like I am redrawing that y-axis here. This is y and this is the amplitude. Then it cannot be like, let's say this is y equals to 0, this is y equals to y, and this is the y direction. So it cannot be, the waveform along y cannot be like that. Or also for x and g also, waveform cannot be like that. Amplitude cannot be non-finite. I mean, it has to be zero at these endpoints. It has to be waveform like this, or these are allowed because your amplitude has to be zero here and has to be zero here. The boundary, this is the physical condition we have to apply. So applying this condition, let's say we apply as we solved here, so here along y. So let me derive the boundary condition for y. So for y we have the expression of wave amplitude here. So and it has to be y 0 has to be 0 according to the physical situation here. So this term go to have to go have to go to 0 because at y equals to 0 this term going to give me 1. So to satisfy the boundary condition I have to let it go to 0, this constant term. So whatever be the constant, so then we are going to get y equals to y times sumta 0 plus sumta sine of ky times y. Again, we have to apply one more boundary condition, that is, again for y equals to ly, it has to go to 0. So y times ly equals to 0. This implies sine of ky ly equals to 0. So we cannot let the amplitude of this term go to 0, otherwise it will be a trivial solution. Our y for any situation is 0, capital Y. So you cannot do that. So then this term has to, I mean, this term have to go to 0. This term will go to 0 when ky ly equals to ly pi. This is the condition we know for sine function to be 0. The argument of sine function will be some integer where ny equals to 0, 1, 2, and so on. For this situation, I cannot consider 0 here because otherwise this will give me the trivial solution. But in the later case, when we will find psi, at that time we can allow it to be 0. I'll show you when I will completely solve the condition. So for similar, with a similar argument, we can show for z and x also that kx times lx goes to nx pi and kz lz equals to nz pi. So from these three equations we can find the k in terms of n and lx. So I'm going kx equals to nx pi over lx, ky equals to ny phi ly, and kz equals to nz pi over lz. So we get the expression of k, and we know that we can write velocity of sound c equals to omega times mod of k vector. This is the vectorial form of the velocity of sound with the wave vector. So basically mod of k will be kx square plus ky square plus kz square. Using these three terms here, we can write it as, and take me phi out of there, it will be like nx over lx square plus ny slash ly square plus nz over lj square. So we get the expression of modulus k. Let me write it like k. So we get the expression of k here, and we can write here equals, so c equals to omega times k, and as omega equals to 2 pi f times k equals to c, and plugging this value of k we can write And rearranging the term from this equation, we can write f equals to c c over c over 2 pi k. I think I made a mistake here. Let me check. Oh, I made a mistake here writing this expression because k dimension of k equals to length inverse. This dimension is of time inverse, so this is not going to give me the dimension of velocity, which is LT inverse. So there is a mistake here. Let me correct it. So expression of velocity is going to be omega over k, and I can write it like c equals to 2 pi f over k, and then this term, and using we can write a equals to c times k over 2 pi, and using the value of k here we can finally write a equals to c over 2 times lx square plus ny square over ly angel square over lj square. So how can I assure you that this expression is the right expression of frequency for the 3D wave? So to do that, we can, as this is a 3D wave, we can also get expression for 1D from here. To get that, let's say our box is one dimensional, then L, Y and Lz goes to, if we set equals to 0, then it should give me the frequency of in 1D L1D. Let's check from here. Does it give me the expression as we derived here? Yes, derived here that for 1D this is a expression of frequency. So if we put, wait a minute, we can, there is a mistake in describing, so we cannot consider it like this equals to 0. We can set it to like it doesn't exist. So how the wave function going to look like? Then this term this term is going to vanish, and this term also going to vanish. Then we are going to get the expression of frequency here, c over 2 times nx over lx, which is arranging this term 2 times lx times lx. And we can verify that this expression of frequency is exactly same as we derived for 1D in the recap part, that I can check that this expression is exactly same as this expression. So our equation for 3D equation of frequency for 3D wave is correct one. Uh, in the next video, I will show you that how can we verify uh, this frequency from using some practical instrument. I mean, I want to say that practical verification of this frequency, I'll show you in the next video that this expression really works in the real life also. I will show in the experiment part of the next video. In the next video. So, so this is the end of the today's lecture.